A very good morning and welcome to my presentation. This presentation is a part of the digital assignment in Theory of Computation course under Professor Dr. Anitha. Myself, Gautham, from Computer Science and Engineering, and I'm here to give a short lecture on connections between automata theory and number theory. Automata theory and number theory may feel like two different fields that are not even related, but there is a deep connection, and this has been an interesting area to study on. As we all know that automata theory is what it deals with the machine and that process output bounded to set of rules for the provided appropriate inputs. And on the other hand, number theory is completely based on numbers and integers, and it deals with the properties and behaviors of them. Now we are going to dive into the connection between the disparate areas. First, knowing about automata theory, it is a study of abstract machines and that deals with the design of automata, and it has the control language and its own predefined grammar and even state transition and table transition with the mathematical models. And coming to the number theory, it is a complete branch of mathematics that deals with wholly numbers involving arithmetic, prime and complex numbers, divisibility, etc. And this mostly helps in cryptography as it helps in developing algorithm and efficiently encrypt and decryption. And number theory has the divisions of natural numbers, whole numbers, integers, and rationals and irrationals, as we can see. And for automata theory, according to Chomsky, it is divided into regular grammar, context free, context sensitive, and unrestricted. And for different problems and approaches, we have discrete level of approaches in automata theory, like finite state machine, which is the most simple approach, and then the push down automata, which has the memory stack in that, and Turing machine, which are more powerful and can solve some complex memory problems using tapes. And number theory mostly deals with the properties of prime numbers, irrational numbers, and rational numbers. And the most popular problem in number theory is the distribution of prime numbers. And even several theories have been proposed to explain it. And modular arithmetic is also an even more interesting concept of number theory, and it is used in cryptography as well. And coming for modular arithmetics, uh, working or like RSA and Diffie-Hellman, and based on the concept, or these kinds of algorithms are mostly based on the concepts of modular arithmetic. And then going through the topics that makes the connections between number theory with the automata theory or distribution of prime numbers, cryptographic algorithm, and computational complexity of algorithm. And coming to the distribution of prime numbers, this is the one of the most complex topics that have been puzzling mathematicians, and still the uh, solution for this distribution of prime numbers has not been yet found, and it's still a million-dollar question. And this lead to many theorems, and uh, this has found the new rules and set of, and this not like this gives an approximation only, and this is the, yeah, finally it's a complex and fascinating topic, which makes open questions and conjectures still wanted to be solved. And cryptographic algorithm, I say, is widely used like for secure data transmissions, and this involves prime numbers and to generate public and private keys. And this This algorithm involves process like key generation, which generating public and private keys as it is in the name itself, and encryption for the message to be encrypted from the center, and decryption after the receiver gets the message, the encrypted message for decrypting, like decoding it, decryption, and the and finally, coming to the larger the complexity in the prime number factoring, the stronger the encryption algorithm works here. And next, algorithm complexity, computational complexity of algorithm. This is the concept that helps greatly to pick the correct and best algorithm to solve a problem that works the most efficient. And this comes under the branching of number theory. And this also does the automata working in finding the best algorithm. And mostly the complexity of algorithm is usually measured using time complexity, the accurate amount of time an algorithm takes to complete, so that we can find an efficient algorithm to solve a problem. And the most famous applications of automata theory in number theorem is the primality test, and this Miller-Rabin test is the most popular one. And here the algorithm works with the main condition of a power n minus 1, which is equivalent to the 1 mod n. And here n is the number, the prime number, and for the each iteration, a random value is taken and applied to A, and which is in turn gives the result of this primality test. And the next application is the modular exponential, and this is here and another mathematical operation, and to calculate the remainder of the power of number, like it is divided with the modulus and to be founded. And in this is mostly used in analysis, design and analysis of cryptographic algorithms and finite state machine and computation of complex arithmetic operations. And this is typically like involves breaking down the exponential into binary forms, so that you can find the you can build the finite automaton and calculate the modular exponent. And even more surprising connections like between number and automaton are in the field of security, coding, cryptography, graphics as well. And automata theory even contributes to number in the mean of factoring large integers, determining primes, and testing conjectures and design of hardware and software. And finally, automata theory and number theory has a strong connection between themselves, and they contribute to many important branches in mathematics. And still more new solutions to problems are being solved using number theory applied in automata, and including the design of efficient algorithm for modular exponential and the study of computation of complexity algorithm. And with this, I conclude and thank you so much for listening to my lecture. And I hope this lecture would have been an useful one to you. Thank you.